watching one of my lessons live. And if you're watching right now, I'd say, you're out of high school, grow up, find something better to do with your time. Anyway, where were we? No, I'm kidding. I'm honored. Anyway, let's get to it. So we learned in the last few days, we mentioned that sometimes things can have fewer than a complete octet. We also learned that sometimes they can have more, but we haven't talked about how that works yet, but we've acknowledged the existence of that. The idea that sometimes we dip into a d orbital or an f orbital to make bigger hybrid orbitals, so we can make more than 4 bonds potentially. So things can sometimes make more than 4 bonds. That's what our last lesson will be about. But all of that is going to lead you to a situation now where sometimes you can draw multiple structures for the same thing. In fact, one of you came up and asked me earlier about, when I did my assignment, I drew a structure, and then later when I Googled that thing, I saw a different structure. Am I wrong? And the answer is, actually, no. I'm hoping that you have the not quite right answer in your assignment 1, because we hadn't learned about these topics yet in assignment 1. So if you somehow magically came up with the one that involves knowing formal charges and how to balance formal charges out, I'll be a little suspicious of your first assignment. I'll be like, isn't it interesting that you knew how to do that when we hadn't learned about that yet, right? If you've already turned it in. But today you'll learn, if I can draw more than one structure for things, how do I know which one to go with, right? How do I know? And the answer sometimes is, there's a clear answer. We actually learned that yesterday. If there's 3 structures that you're able to draw, but some of them have formal charges and some of them have no formal charges, which one's the correct one? The one with either the lowest formal charges or ideally the one with no formal charges. And we looked at that yesterday, right? We said carbon dioxide could be drawn like this. Or it could be drawn like this. Those are both drawings that satisfy... what am I doing? Could be drawn like this. Those are both drawings that satisfy our rules for Lewis structures, right? If we count 2, 4, 6, 8, 10, 12, 14, 16 electrons on the left, 2, 4, 6, 8, 10, 12, 14, 16 electrons on the right, and that's what we should have. Everything has a complete octet. It's all good, right? The difference is, in this case, the formal charge on this oxygen, we can tell just by eyeballing, how many bonds do we expect oxygen to make? How many is it making? 2, so this has a formal charge of, if it's following our rules, 0. How many bonds do we expect carbon to make? How many is it making here? So its formal charge will be 0. And here, just like that one, we expect it to make 2 bonds. It's making 2 bonds, so its formal charge will be, again, if you can't eyeball that, no problem. You could have said oxygen has a valence of 6 electrons, right? We subtract the bonds, and it's making 2 bonds, and we subtract the free electrons, that's 4, and it comes out to 0. So if you need to do the math on it, you can do the math on it, no problem. But do we see that? This structure has no formal charges. On the other hand, this over here, carbon. How many bonds do we expect carbon to make? 4. How many bonds is carbon making? What's its formal charge going to be? 0. Good. But both of these oxygens are weird, right? And let's actually count them. Oxygen has a valence of 6, right? How many bonds is this making? 1. And how many free electrons does it have? 6 free electrons. What will its formal charge be? -1 is its formal charge. And what about this oxygen? I bet you can predict right now. We know the formal charges have to add up to the charge of the compound. So you could probably just guess what it is. But let's just count it. Oxygen has a valence of 1, 2, 3, 4, 5, 6. So 6 is the valence. How many bonds is it making? And how many free electrons? And so what's the formal charge on this one? +1. Good. Which means this structure has formal charges. And that means that in nature, we will see this structure, and in nature, we would expect to not see this structure. Does that make sense?
But for the wrong structure of carbon dioxide, the total formal charge would be 0. But for the others, it's not. Why? Like, if it's the wrong structure, then
It's not the wrong structure. It's not a wrong structure. It's actually a legitimate structure. Because like you pointed out, the formal charge is balanced out to 0. The charge on the thing is 0. That is a thing that can happen. So it doesn't occur normally, and even that's a bit of a lie. What it doesn't occur is often. So in 100 billion carbon dioxide molecules, one might look like that, and the other 100 billion will look like that. It is that this is much more energetically favorable, so this is going to actually happen often. This is energetically unfavorable, so it will happen rarely. But a good thing to know about the universe around us, if something can happen, there's something called the law of big numbers. This is a genuine mathematical law, and it's called the law of big numbers. And basically it says that the bigger your numbers get, it becomes a certainty that rare things will happen. If there's a 1 in a billion chance of something, then we'd expect 8 people on Earth to have that happen to them. But if there's a 1 in 100 billion chance, probably it's never happened to anyone on Earth. If there's 1 in 100 trillion chance, it's really unlikely that's happened to somebody on Earth. But if there were 6 billion trillion people on Earth, we would expect it to happen. Does that make sense? There are a lot of atoms in the universe, which means that this structure, even though it's energetically unfavorable, will happen, but it's going to happen so rarely that as a chemist, you can functionally ignore it. Does that make sense? That's the true answer. And so the easy answer is just to say that doesn't happen, that happens. The real answer is more nuanced than that, where we say there's a high probability that that happens and a low probability that this happens. Is that fair? Did that answer your question? Okay. Did that confuse everyone else? No, we're good? Okay, good. But sometimes you can do more than one structure and they're actually all valid. In this case, only one of these structures is ideal. And I shouldn't have even said valid, I should have said equally valid, right? It's not that this is an invalid structure, it's just a less valid structure. It's a less common one. But sometimes they'll be equally likely. Let's look at, not carbon dioxide, let's look at carbonate. Okay? We know the rules. We count electrons. Carbon has how many electrons? 4 valence electrons. And oxygen has 6, and there's 3 of them for 18 electrons. And this thing has a charge of -2. So that shall be 2 more electrons for a total of 24 electrons. Okay. We know that carbon's going to go in the middle. We know that oxygens are going to go around it. And we know that there's going to be a lone pair, right? Oh, well, we don't know that yet. We eventually, in fact, I don't think there is going to be a lone pair. So now let's count. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Count electrons. How many do we have? 24. So that's all we get, right? So now, up till now, we've just said pick an oxygen, make the double bond there, right? But the truth is, there's 3 different things that can happen here, right? Which is maybe the double bond happens down here, right? Or we could get the same structure, but the double bond could happen over here, right? Is that just as valid? Or, where else could it happen? Over here, right? And the truth is, I haven't drawn any of these with the proper shape. What shape should this be? It should be trigonal planar. The bond angles should be... you tell me. Pyramidal or planar? Let's try that again. Pyramidal, or planar? Which one?
Is there a lone pair?
Is there a lone pair?
There's no. So it's just planar.
We have a pi bond. Pi bond means what's our hybridization state?
SCH4U.
sp2. So actually, if we're drawing these accurately, we should be drawing them at 120 degrees. Don't bother changing yours if you've already drawn it. It's not that important for what we're doing right now, but that's a better structure, right? Because our hybridization state isn't sp3, it's sp2. So the bond angle between them ought to be, what? 120. Again, I wouldn't change your drawing if you've already drawn it. It's not the important part right now. Did you? Look at you. What a kid. Makes me proud to teach all y'all. All y'all. That was very folksy of me. I'm very folksy. Okay. And of course, each of these has a charge of what? -2. Okay. Those are equally valid. Is there any reason to prefer one over the other that you can think of? I can't, right? In fact, this molecule is perfectly symmetrical, which means that there's no advantage to one placement or the other. They should all be equally likely. And they are all equally likely. A third of the time this bond forms, it will form like this. A third of the time it forms, it will form like that. And a third of the time it forms, it will show like this. All right? So, there's two ways to show this. The first is to draw all three structures. As above. I'm not going to redo that. So if you want to, anytime that there's multiple structures available, you can draw all three. But here's the thing. A double bond is actually a shorter bond than a single bond. If you think about it, makes sense, right? There's not only the sp3 hybrid orbitals overlap, but so does the p orbital, right? And so it closes in. It becomes a shorter bond angle. So we would expect that in the carbonate ion, we would get one of the bond angles being shorter. But actually, it doesn't. Because what we find is that all three of these bonds don't just happen. They actually all happen in the same molecule. Because the double bond will shift from this oxygen to this oxygen to this oxygen, and it will do so randomly. But if you do something randomly, here's that law of big numbers again. If you do something randomly where all three outcomes are equally likely, then they will average out to happening the same amount of times. Does that make sense? And so what we end up with, and how we usually draw this, is carbon to oxygen, oxygen, oxygen. And we draw these little dashed lines here. How did I draw that last time? Because that looks hideous to me. Did I do dashes or dots? I bet I did dashes. I want to check. Yeah, dashes are better. Okay. Where did I? Oh, back up here. Back up here. That's not me. That's me. I thought that looked weird. So we do dashes like that. And now, I should say too, instead of the word or, we typically will draw this arrow that looks like this. And that arrow means that it can transition from one state to the other. It can transition from one state to the other. And because it can transition from one state to the other, we tend to draw it like this. When we draw a resonant structure, which is what this is called, we don't attempt to draw in the lone pairs because they will obviously change, right? Does that make sense? So we just draw the bonds, no lone pairs. The whole thing has a charge of -2, right? But now think about it. If everything has to make that, this bond is only there 1/3 of the time. And this bond is here 1/3 of the time, and this bond is here 1/3 of the time, right? Which means this has a formal charge of what? This is where it gets weird. This has a formal charge of 0 1/3 of the time, and -1 2/3 of the time, which makes it have a formal charge of -2/3. In other words, 2/3 of the time it doesn't have that extra bond. Does that make sense? And this one will have a formal charge of -2/3. And this one will have a formal charge of -2/3. Does that make sense? Which means 2/3 of the time there's no bond here. 1/3 of the time there is a bond here. Does that make sense? And if you to get that number, ready? The way we would do it is, what is oxygen's valence? Okay, 6 valence. Now, minus bonds. What bonds does it have? It has one bond all the time, and then it has another bond, how often? 1/3 of the time. That's brutal, right? Can we all agree that's brutal? Okay. Now, this is not actually what I recommend. And then, how many electrons does it have? Well, this is where it gets weird, right? It is always going to have 2, right? Right? And then, the other lone pair, it has 2/3 of the time, right? Which means minus 2/3 of an electron, minus 2/3 of an electron. Now, do you actually want to do the math this way? Absolutely not, right? That's miserable. But if you do all that math, what you're going to find is that you end up with -2/3, right? Okay, listen. You're never going to want to do this math, right? You're never going to want to do this math. You can. Do we see that there? But what we'd usually do instead, what I'd usually do instead of this math, which is miserable, don't do it, all right? Miserable math, don't do it, is we can just look at the formal charges here. Does that make sense? What's the formal charge here? Well, we already looked above. If oxygen is only making one bond instead of 2, but we can do it. 6 valence minus 1 bond minus 6 electrons has a formal charge of -1. This one has a formal charge, obviously, then also of -1. And this one's following the rules, so its formal charge will be 0. Okay, so the actual math we want to do is easy. Since it switches between these 3 things randomly, we can just take the average of those 3 things. Does that make sense? So the formal charge will be the average of the resonance of the structures. Does that make sense? Just look at the structures above, and if you take the average, that will give you the formal charge here. Does that make sense? So if you look up here, the formal charges are -1, -1, and 0. What's the average of -1, -1, and 0? You can plug it into your calculator. You add them all together and divide by 3, right? What's -1 plus -1? -2. What's -2 divided by 3? I mean, you could write it as a decimal, but don't. Just write it as -2/3. Does that make sense? So you could do miserable math like this. My strong advice is don't. In fact, you know what I'm going to do? I'm going to erase that. Because it works, and I want you to show you that it works. If you go like, well, where the hell does that come from? But what I would actually do is say, to get formal charge, average of -1, -1, and 0, which is -1 plus -1 plus 0/3, which is -2/3. Is that cool? Does that kind of make sense? So what we're saying is, if there's equally plausible structures, not only do they all happen, but actually they will happen in the same molecule. The molecule will shift from one structure to another. That's what our research shows us. That if structures are equally valid, then they will occur with equal frequency even inside the same molecule. As the electrons orbit, it is perfectly valid for them to shift their orbit to form the second stable structure and to form the third stable structure, and they will move back and forth between them. You don't have to get too stressed out about it. Just find all the valid structures, and if they're equally valid, then we can just draw these dashed lines to show that they're equally likely. Does that make sense? But the only reason these are equally valid is because in each case, the formal charges are the same. This is a formal charge of -1, -1, 0, and 0. -1, -1, 0, and 0. -1, -1, 0, and 0. Because they all have the same formal charges, they're all equally likely. If we could draw a third structure of this, I'm sure we could. Like I could draw this structure here, carbon, oxygen, oxygen, and just put lone pairs of electrons around all these. That's also a structure, but the reason this doesn't become part of our resonance structure is because here the formal charges would be -1, -1, -1, and what would carbon's formal charge be here? Carbon has a valence of 4. How many bonds is it making?
3.
How many lone electrons does it have?
2.
For a total of
Plus 1.
+1. That's a possible structure, but it's got more formal charges than any of these do, so we can ignore it. Does that make sense? Is that cool? Yeah. No, because remember, don't forget the count electron step. In this case, once we're up to 24 electrons, that's all we get. Sorry? That's right. That's right. That's when normally we'd make a double bond. So you see, one of the possibilities is just to leave it and just have carbon not have enough electrons. And that actually is valid. That happens sometimes. We just drew it and we saw it's less valid than any of these. And so it gets excluded. It's not that it's impossible. It's just that it's way less likely. Does that feel terrible? Awful? Vile? Horrible? Yeah? It's okay. It can. This stuff's confusing. It's tricky. It's weird. But hopefully with a bit of practice, we'll get there. And again, this does not feature heavily on your unit test. This is like, a lot of teachers skip this. Some years I skip it and give it to you as lessons you can teach yourselves. In fact, if you look at the file name, it says Reach Ahead lesson, where some years I give these as assignments if you want to be more ready for university. A lot of teachers just skip this in high school and know that you'll get it in university. I prefer that my students get there and be ready. But I think there's maybe one question about resonance structures on the test for 1 mark, like a multiple choice. So it's not a big deal right now. But I just want you to be aware of it. It's something to know that actually the best answer is that all 3 of these structures are possible, all 3 happen. On the test, if I ask you to draw this and you just drew me one of these, I'd give you all the marks. But if you drew this, I'd give you all the marks and put a little smiley face and say, like, good job, you. On the test, I only care about resonance structures if I ask about it specifically. Is that fair? But once you go on in your chemistry career, they'll always want you to be aware. By the way, if you Google the structure of carbonate, most likely it will actually just give you one of these. But the best answer is actually this one, the resonance answer, because the true answer is that all 3 structures are possible. But like if we Google it right now, I wonder if one of the top hits has the resonance structure, and probably it won't. So you can see this one showing the resonance structures, right? See that? They're showing it with the double arrows between, showing that all 3 structures are equally likely, which is a valid way to draw it. And a lot of students prefer to draw it this way because they don't have to figure out the fractions, right? Just show all 3. Then you don't have to do any fraction math. This one's showing that. I can't find a single one showing the actual resonance. This is another way of showing resonance, but don't worry about that. Yeah, the most common way you'll see it is like that, but the dotted line approach is also acceptable. So do we see how there's the 2 ways to show it? You can either show all 3 structures and show with arrows that we can switch between them, I wonder if I search for resonance structure of carbonate, we'll get at least one that shows the dashed lines. No, that's okay. The bigger a molecule is, the more likely they are to show. Sorry, did I miss one? Ah, there it is. So there's one to show you. Do you see that? So again, just as valid to say these are the three valid structures, there they are, or to show it this way. Either or. Is that cool? Questions? Okay. Can we carry on? We're almost there. Resonance structures only involve moving pi bonds. We can't change the order in which atoms are bound when forming pi bonds, nor can we add or take away electrons. In other words, each structure must obey the rules of making a Lewis structure. But every resonance structure is a valid structure. So as long as you can draw it following the rules, it exists. But we only report structures with the lowest formal charges. And just really quickly, e.g., if you found that you wrote this a little bit too big, what you could do is you could just highlight it, just like this, and you could just shrink it down some, right? Like just like that, and then it's going to fit beautifully. Just a thought, something you could do. You don't even need to draw this example if you don't want or if you don't find it helpful. But remember we said this structure here actually does follow the rules, right? Like it has the right number of electrons, there it is, but it leaves us with everything having a formal charge, whereas these three, only two of the oxygens have to have a formal charge. So that's preferable. Is that cool? That feels all right? Okay. I might even add in the little negative ones. That'd be -1 formal charge, -1 formal charge, -1 formal charge. But this would be negative. Oh golly. Did I just in the wild say oh golly? It's very folksy of me. I feel wild right now, like a wild animal. Oh golly. Okay. So interestingly, this doesn't have higher formal charges. They still only get as high as 1 and -1, but it has more formal charges, so we ignore it, right? We choose the structure that has fewer and smaller formal charges. Oh, I wondered why I felt so space cramped when I was doing the charges. Where was I supposed to do the charges? Here. I was supposed to do it here. But we've done chlorate. That's boring. Should we do a different one? Does nitrate have resonance structures? I think so. We're not going to phosphate yet. Phosphate gets weird. That's tomorrow's lesson. Does nitrate have a double bond? I think so, right? Yeah. Okay, so let's do nitrate.
Or nitrite.
Let's do nitrate. I don't know. We'll find out. Okay, so nitrogen gives us how many electrons?
5.
5 electrons. 3 oxygens will give us how many? 18. And a charge of -1 will give us 1 electron. And that is a total of 24 electrons. So we're going to need a double bond, so that's good. So we could draw the Lewis structures thusly, right? Nitrogen in the middle. And we know we're going to have a double bond, so I'm going to jump right to that 120 degree, right? Obviously, we wouldn't know that if we were inexperienced with this. But I draw the electrons in, and I find that when I've drawn all the electrons in, I have 24, which means I need to form a double bond. So I could form the double bond here. That's one of the options, right? What's another option? I could do it on the top one. Oh, nope. Or I could do it on the left side one, right? Okay. And again, the back and forth arrow tells us that all 3 of these structures coexist. That actually, if you form the nitrate ion, these will all flip between, right? And note what structure I don't include is this one. And why don't we include this one? That's right. Because in this case, if you take the formal charge of everything, you should be used to this by now, but if not, we can count it. All these oxygens are the same, we can all agree. Is that cool? In this case, this oxygen has a valence of what? Valence of 6. And then is making how many bonds? 1 bond, and has how many free electrons? For a total of -1, which means all of these have a charge of -1. Nitrogen has a valence of? It's making how many bonds? 3. How many lone electrons? For a charge of +2. That won't form. You'll never get something with a +2, right? Hypothetically possible, but in practice you will never see it. So we can exclude that structure. So there's only the 3 valid structures. Does that make sense? Okay. So if there's only 3 valid structures, now if we want to find the formal charges, the easiest way to do so is just take the average formal charge for each atom in the valid structures. And that's not as brutal as it seems, because you'll see that really you only have to do the calculations once, because each of these is just a rotation of the other. Does that make sense? So if we go up here and do the math, if we do the math in the first one, then the other 2 are going to have the same numbers, just in different spots, right? And again, if something's following the rules, we know it has a formal charge of 0. Is there anything in here that's actually following the rules? Yeah, this oxygen has a formal charge of 0, because it's following the rules. It's making 2 bonds, and we would expect oxygen to make 2 bonds. If you can't eyeball that, no problem, do the math, right? In fact, let's just do the math. This oxygen has a valence of 6. How many bonds is it making? 2. And how many electrons does it have? 4, and that comes out to
0.
0. Okay, which means that in each structure, the double bond to oxygen has a value of 0, right? We're cool with that? Okay. Now, what about here? What's the valence? Valence of oxygen? 6. How many bonds is it making?
1.
And how many electrons does it have? For a total of?
-1.
-1. So that means everywhere we have a single bond to oxygen, we have a formal charge of -1. Is that okay? That comfortable? And that includes this one up here. And then what about nitrogen? What's nitrogen's valence?
5.
5. How many bonds is it making? 4. How many electrons does it have?
0.
Which gives it
1.
+1. And it's going to have a +1 in each of these structures. Does that make sense? So now, if you want to find the balance, when you want to do the resonance structure, if instead we want to draw it this way, we can say here's nitrogen, right? And it's making a bond to oxygen, a bond to oxygen, and a bond to oxygen. But this bond is going to be a resonance bond, which means sometimes it'll be a double bond, sometimes it'll be a single bond. We can fill in the values. So let's go. What's the average for nitrogen? What's the average of +1, +1, and +1?
0.
Don't want you marking my tests. What's the average of +1, +1, and +1? If I gave a quiz to 3 people, and this person got 1, and that person got 1, and that person got 1, what was the average grade? 1. Good. If you're not sure, what do? Add them together and divide by how many? 1 + 1 + 1 is 3. 3 divided by 3 is 1. Okay, good. Does that feel all right? Okay. Now, what about this here? This up here is -1, 0, and -1. When we add those together, we get -2, right? -1, 0, and -1 adds to -2, and we divide it by 3, so that'd be -1 plus 0 plus -1, right? Divided by 3 is -2/3. And can you see that we do that for each one? This one would be -1 plus -1 plus 0. And if we divide that by 3, we get -2/3. And this one over here would be 0 plus -1 plus -1, which is -2. Divided by 3 is -2/3. And that's the resonance structure. By the way, does that sum to -1? -2/3 plus -2/3 plus -2/3 is -6/3, which is -2. Plus 1 is -1. So it adds up. It makes sense. How's that feel? Not too bad? Just bad enough? Okay. There's some homework. Just practice. Draw me the formate ion. Draw me... By the way, if you want a note here, put carbon in the middle.
What does it mean by cycle?
Cyclo means that the 4 carbon atoms make a ring. I like this structure. This is a real structure. I will draw this for you to start. Let's count. Do you want to do this one together? This is a fun one. Or do you want to be challenged? I will show you the basic structure, but not where any of the bonds go. Cyclo means that the carbons make a ring. You're going to have to figure out where the hydrogens go. I think that's pretty obvious. Whereas we have 4 hydrogens, where are they going to go?
With
Each carbon will get a hydrogen. And I'll let you go from there. That's a real thing. Cyclobutane. Isn't that a fun-looking molecule? Cyclobutadiene. Pardon me. This is cyclobutadiene. Cyclobutane is something a little different. Well, you're going to have to figure out if there's pi bonds. That's your job to figure out. You know how to do it?
No, if there are no pi bonds, there would be no resonance structure, right?
That's right. You cannot have a resonance structure without pi bonds, because it's the pi bonds that move. And again, don't try to put the electrons in your resonance structure, because you have to draw like little imaginary electrons that come and go. Don't worry about that. So try this. Now again, look at me. Do I expect you to be good at this yet? No. So don't be discouraged if you're finding it challenging. It's challenging. And don't be annoyed, don't be discouraged by the 2 people in the class who get it super quick, because there's always 2 people in the class who get it super quick. So don't compare yourself to them. I always say you want to pick a medium-sized person in the class and beat them up, and you want to pick a medium-smart person in the class and compare yourself to them. And if you really want to feel confident one day, pick a small person and beat them up. Or pick a dumb person and compare yourself to them. I'll let you decide who that is. Obviously nobody in this class, but maybe in other classes. That's a joke, by the way. So if you're listening at home, that's a joke, all right? I'm only kidding. Obviously, I don't mean that you should beat up on small people. Anyway, carry on. Do you think